Okay, so now let's start, my dear students, let's start in a smooth start in our solid state electronic course. Actually, if you remember my beginning of this presentation or this lecture, I have mentioned that in order to start understanding electronic devices, I mean here the diodes and transistors and so on, we have first return back to the material. I believe you already deal with the material in different, maybe chemistry and physics courses you have already enrolled in, either in your high school or maybe on your prep year. Now we will start again from the bottom, which is what the physicists say that this is the atomistic level, the atomic level. In this smooth start in our lecture zero, we are going to have a very short journey inside the material and try to see how atoms are arranged in different materials. This what we can call the crystal lattice structure of the material. So what is the crystal lattice? Before going into details, I have just to highlight that in order to read more about the crystal lattice structures, you can refer to our first reference, which is Principle of Electron Material and Devices. You will go to Chapter 1, Section 1.9, or you can go to Solid State Electronic Devices by Streetman, Chapter 1, Section 1.2. Here you will find more about the crystal lattice structures. Okay, so what is the crystal structures? As all of you know, any material consists of a series, billions of electrons. Of atoms, I'm sorry. And these atoms are arranged by way of one another. So, first of all, we can classify our material into two big classifications, into two big families. What's called a crystalline material, and what's called a non-crystalline or amorphous material. In the crystalline material, we have some sort of periodicity. I mean, atoms are arranged in a periodic way. There is some sort of repetition in the atom arrangement, and that's why we call this as a crystalline material. However, if we have a random distribution of the atoms inside the material, we will call that this material is an amorphous or a non-crystalline material. So this is the main two big families in the material. Actually, in most of our course, or let me say in all of our course, we will deal with crystalline material. This is actually due to two main reasons. The first reason is the main electronic industry is implemented using silicon as a material. You know, of course, Silicon Valley, for example, in USA, and so silicon is the main material used in electronic fabrication. And while you are dealing with silicon, we are dealing with silicon as a crystalline material. So we are more interested with crystalline material. By the way, there is a amorphous silicon, but maybe this will not be covered in our course. On the other hand, the study of the crystalline material is much easier than the study of the amorphous material because you are dealing with a symmetric medium, a periodic medium, a medium with some sort of repetition. So you can just pick up one unit of this system and study it, and this unit will represent the whole system. That's why we will go with the crystalline material in the rest of our course. So let's turn to the crystalline material. As I just mentioned, the crystalline material is a periodic material. It can be periodic in the x direction, in the y direction, in the z direction, or in the three-directional, which is the highest way or the highest order of a crystalline material. So if our material is periodic in the x direction, in the y direction, and in the z direction, you can simply pick up one unit of repetition, or what we can call it the period. You can pick up one unit and then you can study this unit. We will call this unit the unit cell. So the unit cell is the smallest building unit of a material at which this unit is repeated in the x, y, and z direction. So if you study this unit, you have a real sample of the whole material, and what is applied on this unit cell is directly applied to other unit cells in the material because simply they are periodic. So this unit cell is a three-dimensional cell because logically the material is three-dimensional. So we will have a direction in X, we will call it a direction in Y, we will call it B, and a direction in Z, and we will call it C. So the ABC is simply the edges of this cube or cuboid, as we will see later on. So we have A, B, and C representing the X, Y, and Z. Now, this is the unit cell of the material. How this unit cell looks like? Is it something standard? I mean, if you pick up, for example, two different materials, should I have the same unit cell for two different materials, or each material has its unique unit cell? Let's see. Here we have different shapes of unit cells. So for example, we have the very simple, what we can call the cubic unit cell. When we are dealing with a cubic unit cell, that's logically mean that A equals B equals C. I mean here, the direction in the X equals to the direction in the Y equals to the direction in Z. That's why it's a cube. And the angles here, the three angles are 90 because the cube has a 90-degree angle. So alpha equals beta equals gamma equals 90. So this is a cube unit cell. So, and of course we have another shapes. It's not only cube. It may be, as here is a tetrahedral unit cell where you can see that A equals to B in the XY plane, but C is not equals to A and B. So here, for example, C is much greater than A and B. It can be also orthomonic units, unit cell, which is A not equal B not equal C. It can be mononic unit cell, A not equal B not equal Z, and one of the three angles is somehow not equal 90. So many different shapes, many different geometrical three-dimensional shapes. So on these shapes, maybe the most famous one is the simplest one, which is the cubic structure. In the cubic structure, it's simple because all parameters are equal. A equal B equal C, and alpha equal gamma equal beta equal 90 degrees. In tetrahedral, this is not the same. In orthomonic, on monoclonic, these are not the same. So the simplest one is the cubic one. Okay. Now our unit cell is cube, but what about the atoms inside this unit cell? Here we have different configurations. These are the most famous configuration. Most probably you have already seen such configurations in your chemistry courses. So we have what's called the simple cube, the body-centered cube, and the face-centered cube. So let's now go more toward the animations. I will try now to use some animations in order to express this such structures with you. By the way, these animations can be easily found in the lecture, in the e-learning page. You can find this animation. So now I have to change my shared screen. So now you can see this simple cube model. Okay. So this is the simple cube model. For here, we have a cube. It's a cube because the direction in X equals to the direction in Y equals to the direction in Z. And the three angles are 90, so it's a cube. And we call this configuration as a simple cube. Simply, we have one atom allocated in the corner of each, allocated in each corner. So you have 8 corners. Cube has 8 corners. So simply, you have 8 atoms allocated in this structure. So this is a simple cube. This is one of the models we can use to represent a system, a simple cube structure or a material, which can be represented in a form of a simple cube. So this is a simple cube. Let's do another example. For another configuration, I just want to reopen my laser pointer again. So now this is a simple cube. For example, let's now move to another example. Let's go to the body centered cube. So this is the body centered cube. Again, the geometry is the same. It's a cube because, as you can see, the x-axis edge equal to the y-axis edge equal to the z-axis edge. So still we are located in a cube. However, the atom arrangement is now different. We have one atom allocated in each corner. And also we have one atom in the center of the cube. That's why it's called a body-centered cube or the BCC. So this is the structure of a body-centered cube. Another example or another configuration. Let's turn to the third one, which is the face-centered cube. Again, our structure is a cube. So we have a x-axis edge equal to y-axis edge equal to z-axis edge, which is A, B, and C. The three angles are 90 degrees. So it's a cube. But again, the atomic configuration is different. Here, again, we have one atom per corner, as you can see. But we also have one atom per face. So as you can see here, we have one here, one there. We have 6 atoms in 6 faces because cube has a 6 faces. So we have a 6-phase atom. That's why we call it a face-centered cube or the FCC. So these are 3 examples for 3 different configurations while keeping the geometry the same, which is a cube. However, the atomic arrangement is different. Now the question is, according to what this atomic difference appears? Based on what this atomic difference appears. So to make this example more and more realistic and maybe more understandable by you, let me first return back to my presentation. I hope that you can now see my slides. And let's again open our laser pointer. And let's go to what next slide. Here is the most famous material we have, is this, which is silicon. As I just mentioned, maybe 95% of the electronic industry all over the world is rolling on silicon. If you remember from your chemistry classes in the high school and maybe in prep year, you remember that in the periodic table, silicon is in the fourth group. I mean, it has 4 electrons in its outermost energy level. And in order to reach a stable state, silicon atom has to have what's called a covalent bond. If you remember, it has a 4 electrons in its outermost energy level, and then it shares another 4 electrons from another 4 neighbors, so that the energy level seems to be satisfied by 8 electrons. So for a steady state condition for silicon, each silicon atom should have 4 direct neighbors. Let's now see this example. Is, for example, this one, I'm pointing this one on the bottom left corner, if you can see my pointer. This atom has 4 bonds, 1, 2, 3, and 4. So the outermost energy level of this atom has 4 electrons. Each atom, each neighbor atom, we call it a direct neighbor atom. Each direct neighbor atom will share with 1 electron. Then we have this covalent bond, and then this silicon atom can be in the steady state. So this is simply the question. Each material tends to reach what we can call the rest state. What I mean by the rest state is the state at which the atom or the material reach a saturation state. For example, silicon needs an atomic configuration so that each atom has 4 direct neighbors. So the atom will be configured in a way that each atom has a four dark neighbor. For example, if you go to this atom, you will find four dark neighbors. If you go to this atom, here are two. It's only two, but please remember, we still have another two here because this is a unit cell and it's extended. So let me use somehow the pen. So please remember that this is extended atomic. So in the atom, oh sorry, in the unit cell, on the top of the current unit cell, we have another two atoms here. So we still have a bond here and bond there. So now this atom still have four dark neighbors. So each material tends to reach the state at which the material have the required number of dark neighbors. And of course, this required number of dark neighbors is directly depends on what we can call the valency electrons, or the electrons is the outermost energy level. So, for example, this configuration is called the tetrahedral configuration. This configuration is a very famous one because, again, this is the configuration for silicon atoms, and we call it the tetrahedral configuration. So let's now try to have an animation to this configuration. So let me change my short screen and close this one and turns to have this configuration. Again, let's open our pointer and let's go. Okay, so this is a tetrahedral configuration. Again, you have this white color lines that indicate the bonds. So for this atom, for example, you can see that we have one bond, the second, the third, the fourth. Okay, for example, if we go to anyone, choose whatever you want, any atom, you will find that it has four bonds. These bonds may be with atoms in the same unit cells, or it may be with atom with the same unit cells and with other. For example, this bottom atom has one bond with another atom in the same unit cell, but still have three bonds with three atoms outside this unit cell. Again, please remember that the material is crystalline, so this structure is repeated in the X, in the Y, in the Z. It's a three-dimensional structure everywhere. So this is, for example, the tetrahedral configuration. Again, this is one of the most famous configuration because it's the configuration for silicon, germanium, and all other fourth group atoms, as we will see. But in our course, silicon still is the most important material for our study. So now returning back to our presentation. Again, this is a smooth starting to our course, something related to chemistry somehow, which is the crystal structure of atoms. Most probably we will not deal with such topics more after that, but this is just a required introduction to make you refresh or flashback your memory with some data related to the atomic structure of the material. Now, again, our razor pointer, and let's now go to the final slide. Here, I just need to thank you very much for this lecture 0 of our solid state course. Please don't forget to feedback us with your comments, what you like and what you dislike in this lecture. This will be open in the last 15 minutes in our lecture on Monday from 10:45 to 11. You can easily log in this platform, and as I mentioned in my lecture, you can easily go into this platform and you can easily pick up whatever you want to tell us about your feedback. Now, this is the end of this lecture, my dear students. In the next lecture, we are going to deal with what's called the semiconductor fundamentals. This is one of the most important lectures in the course, and maybe it's one of the most important lectures in your understanding to the electronics, because we are going to distinguish between what's meant by semiconductor materials, conductors, and insulators, how we can distinguish between these structures either from a chemical, physical, or electrical point of view. And also we are going to deal with what's called the energy band theory, one of the most important semiconductor theory all over the world. So thank you, my dear students. See you next lecture, inshallah. Thank you very much for your attendance, and hope that you hope that you can we can see you next Monday, بإذن الله. Thank you.